Good afternoon everyone. In last lecture we have seen torque. Before that we have seen the concept of center of mass of two particle system, the coordinates of center of mass. These are the very important concepts related with rotational dynamics, especially rotational motion. As per your 12th standard syllabus, I already said that it includes, that first chapter of 12th standard syllabus includes two parts. One is circular motion, second is actually rotational motion. So the circular motion, some part is included in 11th standard syllabus and some part is included in 12th standard syllabus. So very small recap or revision about 11th standard syllabus of circular motion, and we will study the 12th standard syllabus. There are few applications of circular motion given in 12th standard syllabus, but initial concepts related with circular motion is given in 11th standard syllabus. So in small span of time I will give you the information or some conceptual correction of the circular motion in 11th standard syllabus. So first of all, definition of circular motion. We have seen how force decides the motion. Once again, first, force and displacement are in the same direction, then it is linear motion. If force is perpendicular to direction of displacement, it will produce circular motion. If object is under the action of two equal and opposite forces separated by small distance, then body does not move anywhere but it starts moving about its own axis. It is called rotational motion. So before that, some concepts related with circular motion. So what is circular motion? Circular motion. So motion of the object along circumference of circle is called as uniform circular motion. Circular motion, not uniform. Uniform you can define like this: the motion of particle along circumference of circle with constant speed. Then it is called uniform circular motion. First, only circular motion. The motion of particle along circumference of circle is called as circular motion. Can you give me examples? Here is one example. Yes, that fan is revolving. The blades are revolving around the axis. The dust particles on the blade perform circular motion. Actually, motion of that fan is rotational, but each and every particle on the blades of that fan performs circular motion. So this is again example of circular motion. It is a horizontal type of circular motion. And if the same fan, instead of being suspended from the roof, if it is kept on table, it will perform a type of circular motion. It will be, yes, vertical circular motion. So giant wheel of merry-go-round, it performs vertical circular motion. Fan, the wheel at that earth pot made, that person makes earth pot, other pot, at that point there is a wheel, it moves in horizontal plane, it is called as horizontal circular motion. There are different types of, different examples of horizontal and vertical circular motion. Some important concepts related with circular motion. Consider a particle moving along the circle like this in, suppose, plane, horizontal plane, in this direction. This is direction of motion of particle. So first, it is center of motion. That object having certain mass is moving at particular distance from this center. It is called as radius. If we draw a vector at its head, it is called radius vector. So first concept is radius vector. How we can define radius vector? The vector drawn from center of circle to the position of particle along circumference is called as radius vector. So radius vector, it is the vector drawn from center of circle to the position of particle on circumference is called as radius vector. In circle, its magnitude always remains constant, but direction changes from point to point. Here it is towards the right, if we draw another radius vector in this side, on this side, its direction will be towards the left. We can draw the radius vectors having different directions but same magnitude. So first is radius vector. Number 2, angular displacement. Angular displacement, it is represented by theta. Consider this is a position of particle, suppose A. This radius vector is also called as position vector. We have seen the definition of different vectors in vector chapter. Position vector is a vector which represents point of position of a particle. So here, while performing circular motion, if particle is at position A, the vector drawn from center to represent position A, that vector is called as position vector of point A. It is also called as radius vector. Now if we draw another vector, this is suppose at B. So this is position vector of point B. CB is again a position vector or radius vector. So initially it was at A. If particle moves along circumference from point A to B, it covers small angle d theta or delta theta, we can say delta theta, small angular displacement. So this angle covered by radius vector in particular time is called as angular displacement. So how we can define angular displacement? Angular displacement is the angle traced, angle covered by a radius vector during the circular motion is called as angular displacement. This is angular displacement. So angular displacement can be written as this theta equal to arc is AB upon radius. So angular displacement theta can be written as arc AB, suppose S by R. As these two are the same quantity, similar quantity measured in centimeter or meter, it is also measured in centimeter or meter. So it has no unit. But we take the unit of angular displacement as SI unit, as radian. This is a supplementary physical quantity. These are two fundamental physical quantities. Ratio of two similar quantity has no unit, but this angle is measured in radian. Also it is measured in degree. So this is angular displacement. One thing must be remembered, very small angular displacement is a vector quantity, but large angular displacement is not vector quantity. Second part is, third concept we have to study here is angular velocity. Angular velocity, it is represented by omega. So as usual, linear velocity, it is rate of change of displacement, linear displacement. Instead of using linear displacement, we can use here angular displacement. To tell me definition of angular velocity, so it is the rate of change of angular displacement with respect to time. In other words, we can say that change in angular displacement per unit time is called as angular velocity. So angular velocity can be written as limit of delta theta by delta t, limit as delta t tends to 0. Actually this is called as instantaneous angular velocity. The concept must be known, instantaneous average. If you have seen we have studied in one-dimensional motion, instantaneous velocity, instantaneous speed, instantaneous acceleration, average acceleration, etc. Similarly here we use instantaneous angular velocity. Generally you can write this omega as d theta by dt. Also you can write this omega as theta by t. So angular displacement can be written as omega into t. We have to use this in number of chapters in different chapters which we have to study later on. So theta equal to omega into t, just like S equal to Vt, displacement equal to velocity into time. Similarly angular displacement equal to angular velocity into time. So this is angular velocity. So unit of angular velocity, it is radian per second. it is a vector quantity. See here, it is a vector quantity and its direction is given by right hand screw rule. You know right hand screw rule. Hold the axis in your right hand, if stretch your thumb denotes the direction of that vector, rotational direction is represented by curved fingers, then stretch your thumb represents direction of vector. So this thumb denotes direction of vector. So angular velocity is directed along the axis. It must be clear. So angular velocity, it is change in angular displacement per unit time. So this is angular velocity. Last concept here, angular acceleration. It is represented by alpha. As linear acceleration, we can define angular acceleration. Linear acceleration can be defined as rate of change of linear velocity with respect to time. Similarly, here angular acceleration can be defined as the change in angular velocity with respect to time, or rate of change of angular velocity. So we can write this alpha as it is equal to d omega by dt, where d omega is change in angular velocity. In other words, we can say that omega 1 is initial velocity, omega 2 is final velocity. It changes in time t. Then this alpha can be written as angular velocity, can be written as this alpha can be written as omega 2 minus omega 1 divided by t. So this is again a very important relation. Alpha is omega 2 minus omega 1 upon t, where omega 2 is the final angular velocity, omega 1 is initial angular velocity, t is time. Depending upon whether omega 1 or omega 2 is greater, acceleration is of two types. If omega 2 is greater than omega 1, this alpha is positive. And if omega 2 is less than omega 1, then alpha is negative. If this omega 2 is less than omega 1, then alpha is negative. It is called retardation or deacceleration. So if we switch on the fan, what happens? Its speed increases, number of revolution increases. At that time, the acceleration produced is like this. Initially, the fan was moving with, suppose, 50 rpm. Its speed increases to 100, positive acceleration. And if finally, when we switch off the fan, what happens? Its speed decreases. If its speed decreases from omega 1 to omega 2, final velocity is less than initial velocity. What happens? Alpha is negative. So this is positive acceleration, negative acceleration. It is also vector quantity. Angular velocity, angular acceleration are vector quantities. Both of these are directed along the axis of revolution of that object. That object is revolving about this axis, and alpha and omega are represented by this axis. That is right hand thumb rule, you can say, or right hand screw rule. So unit of this angular velocity is, angular acceleration is, it is radian per second square. So this is angular acceleration. Now if you get clear this concept, then we can use the kinematical equations which we have used in terms of linear velocity, linear acceleration. The same kinematical equations can be written, can be used in terms of angular velocity. So we have the three kinematical equations. First is v equal to u plus at. Second is s equal to ut plus half a square. Third is v square equal to u square plus 2as. Where? Tell me the name of these terms. What is v? Yes, final velocity. U, initial velocity. Small a, yes, it is acceleration, and t is time. So similarly, if angular velocity of object increases from omega 1 to omega 2 in time t under constant acceleration alpha. It covers small angular displacement theta. Then the kinematical equations for angular motion, it may be used in rotational motion also and in circular motion also. That is why it is the very important part as far as the rotational dynamics is related. The study of rotational dynamics, for study of rotational dynamics, these concepts are very important. So kinematic equations can be written as omega 2 equal to omega 1 plus alpha into t. This is first kinematic equation. Second, instead of s, we can write theta is equal to omega 1 into t plus 1 by 2 alpha into t. Just replace small a, linear acceleration by angular acceleration, linear velocity by angular velocity, and finally omega 2 square equal to omega 1 square plus 2 alpha into theta. So here omega 2 is final angular velocity, omega 1 is initial angular velocity, alpha is angular acceleration, and theta is angular displacement. So these are the concepts related with circular motion. Starting from definition of circular motion, the motion of particle along circumference of circle is called as circular motion. If the motion of particle along circumference of circle is with constant speed, it is UCM, uniform circular motion. And if the motion of particle is along the circumference of circle but with different speeds, magnitude, changing magnitude, then it is called as non-uniform circular motion. Any vertical circular motion is non-uniform, any horizontal circular motion is uniform. Motion of a planet around the sun is considered to be circular motion. It is uniform circular motion. Motion of merry-go-round, giant wheel of merry-go-round is vertical circular motion. Wind wheel, the motion of the blades of the wind wheel is also vertical circular motion. It is a non-uniform circular motion. So uniform circular motion, non-uniform circular motion. There are different types of circular motion, vertical and horizontal. Generally, maximum part is used as horizontal circular motion, but applications of circular motion, there are again few examples. We have to use that wheel of death, मराठीमध्ये मौत का कुआ त्याला म्हणत असतो आपण. It is also example in which you have to study the different concepts, different speeds at different points. So that is vertical circular motion. So these are very important concepts related with circular motion. So this is just introductory part to again rotational dynamics. Now we will study actual syllabus of 12th standard from tomorrow. Thank you.